You ever watch an athlete do some incredible spin or flip and just think, how do they do that? It seriously looks like they're breaking the laws of gravity. But what's really happening is that they've become masters of physics. So let's dive in. Okay, picture this. A figure skater is gliding across the ice in a slow, elegant spin. And then, without pushing off again, without any obvious help, they suddenly accelerate into this incredible, lightning-fast blur. How is that even possible? I mean, where does all that extra speed come from? Well, that's the big mystery we're going to solve today. All right, so to figure out the skater's secret, we've got to go back to basics. We're talking about the fundamental rulebook for how everything moves, written about 350 years ago by Sir Isaac Newton. His 3 laws of motion, they're the foundation for everything an athlete does. So, law number 1 is all about inertia. The easiest way to think about it is that, well, objects are kind of lazy. A soccer ball sitting on the grass is going to stay right there, and a hockey puck sliding on the ice is going to keep on sliding, unless something, like a kick or a hockey stick, messes with it. Simple, right? Things just want to keep doing whatever they're already doing. That brings us to the second law. If you want to change how something is moving, you've got to apply a force. And that famous little equation, F equals ma, basically tells us that the heavier something is, the more oomph you need to get it going. It's why you have to kick a bowling ball way harder than a beach ball to send it flying. And the third law, this one's crucial. It tells us how athletes actually generate force in the first place. See, forces always come in pairs. When a swimmer pushes back on the water, that's the action. The water pushes the swimmer forward with an equal force. That's the reaction. And that's what makes them go. Okay, so those are the rules for moving in a straight line. But our skater is spinning. And it turns out all those laws have a rotational equivalent, a special version just for spinning. And that is where we're going to find all the clues to our puzzle. Our first clue is something called torque. So if a force is a push or a pull, you can think of torque as a twist. You create torque whenever you apply a force that isn't aimed right at the center of something. For a skater, this is how they get the spin started. They don't just push straight off the ice, they push at an angle to create that initial twisting force. That's the torque. Now, for what is honestly the most important clue of all, the moment of inertia. So if regular inertia is an object's resistance to being pushed, moment of inertia is its resistance to being spun, its rotational laziness. But here's the really cool part. It's not just about how much you weigh. It's about where that weight is. And this is the athlete's secret weapon. Just look at this. When a skater has their arms stretched way out, all that mass is spread far from their center. That creates a high moment of inertia, which makes them really hard to spin. But the second they pull their arms in tight, they bring all that mass close to the center. That gives them a low moment of inertia, making it way, way easier to spin. They can literally change their own rotational laziness in an instant. So let's review. We have torque, which starts the spin. We have moment of inertia, which is the resistance they can actually control. We have all the pieces of the puzzle. Now it's time to put it all together with one of the most beautiful rules in all of physics. And it all comes down to this one simple-looking equation. Angular momentum, which we call L, is basically the total amount of spin an object has. You get it by multiplying its moment of inertia, I, by its angular velocity, omega, which is really just a fancy way of saying its spin speed. And here it is. This is the spinning version of Newton's first law. What it means is that once our skater is gliding freely, with no more pushes or twists from the ice, their total angular momentum, that L value, is locked in. It is conserved. It has to stay the same. It can't just change. So let's just walk through it step by step. 1. The skater pushes off the ice. That gives them a fixed amount of angular momentum, L. That number is now set in stone. 2. They pull their arms in. We already know that this makes their moment of inertia, I, go way, way down. 3. Now the law of conservation kicks in. That total L value cannot change. So if I just dropped, something else in that equation has to go way up to keep things balanced. 4. And that something is omega, the spin speed. It has to skyrocket to make up the difference. It's not magic, it's physics. And you know, once you understand this, you start seeing it absolutely everywhere. The figure skater is such a perfect example, but this isn't some rare trick. It's a fundamental skill that athletes in tons of different sports use to control their bodies in the air. I mean, think about it. Divers tuck into a tiny ball so they can spin faster and squeeze in extra somersaults. Gymnasts do the exact same thing during a floor routine.
A high jumper does this amazing thing where they arch their back so their center of mass actually goes under the bar while their body sails over. Even BMX riders will shift their bodies to control their bike's spin mid-air. They're all manipulating their moment of inertia. So the big takeaway here is that these incredible athletes have this deep, intuitive understanding of physics. They aren't defying the laws of nature at all. They are using them, exploiting them to do things that look impossible. Just by changing their body shape, they become complete masters of spin.
So now you can spot it happening on the field, in the gym, on the ice. But what about a little closer to home? How does a cat, if it's dropped upside down with absolutely no spin at all, somehow manage to twist in midair and land perfectly on its feet? Well, the answer is just another beautiful example of these very same principles. A cool little puzzle for you to think about. Thanks for joining me.